Hello. Right, so next up we've got Edward, who's going to be talking about artificial intelligence and security and the way you can break things using AI. And he's a university student at York. Kind of. So over to you.
Hi everyone, can you all hear me alright? Yeah. Excellent, great. So yeah, my name's Edward Bowles, not Bowles, that happens surprisingly often. I am currently in the middle of doing my PhD at York, but I stopped for about a 6-month period to work full-time as a pen tester for Sec 1 APT. Going to be moving to part-time. What my PhD is about is using some of the techniques which I'm going to be talking about to find interesting and cool and ultimately totally useless attacks against crypto. However, the techniques themselves are quite useful, and they're ones which you don't really tend to come across in the industry quite so much. One slide summary so that some of you can still make the fishing talk. Some problems in security are really hard. There are many of them. Finding bugs, like automated bug finding in software, really difficult. Coming up with decent IDS rules, really, really difficult. Some of the techniques which I'm going to be talking about can help you. The techniques aren't really that hard. You know, there's some long words, and some of the explanations that you're going to find online are really confusing. But ultimately, once you kind of dig past the acronyms, there's some. It's pretty straightforward, and you can use it pretty reasonably. Also, there are lots of tools you can use. Admittedly, most of them were written by academics. However, they have been used a lot, and that's a kind of testing in itself, I suppose. Why should you be here and not somewhere else? Artificial intelligence is a very big deal. It's unfortunately not a thing. It's rather a collection of various interesting techniques, some of which are applicable to security, some of which are not. I'm going to be talking about the ones that are. Ultimately, the thing about artificial intelligence is it really boils down to a problem with search. You have some kind of problem. You want a tool to do a thing. You can kind of recognize when your tool is doing the right thing, but you don't necessarily know how to create it yourself. Get a tool to generate one for you. Some people have done exactly that, some really interesting stuff. I'll talk about those to give people some inspiration. And also, I won't quite give you pseudocode, but I'll give you enough information that non-technical people will understand, and the technical people can go away and actually implement stuff, which I feel like is a reasonable balance. Artificial intelligence in general. For those of you who don't know, AI is essentially the science of it'll do. There are really difficult problems. We don't know how to solve them. We don't know how. We might be able to solve small variants of those problems, but the kind of instances of those problems that you get in real life are just too complex. We can't deal with them. Some of these problems are they're in the complexity space of NP, which means they cannot be solved by a non-deterministic Turing machine in polynomial time. What that means is you can't solve them for big instances. Not possible. Whenever you see NP, just replace it with those two words, and it'll make the paper make sense. For example, one is called the Traveling Salesman. Who's heard of the Traveling Salesman problem? Yeah, who knows how it works? As in, who doesn't need an explanation? Okay. Well, for those of you that do, imagine you've got a map with a bunch bunch of cities, a bunch of roads connecting them, and you want to start off from the city you're in, go to every other city once, and come back to where you started in the most efficient way possible. If you have, we can generally solve them for about 100,000 cities, but we're talking massive amount of computing power required to find ideal solutions. However, we don't necessarily need the best solution, especially if it's going to take you decades to come up with. You can use some of these search techniques to find what are called heuristic solutions, i.e. they roughly approximate the best solution. They're pretty efficient, maybe only like 2 or 3% difference between the best solution and the good enough solution that you've come up with. And you can use the kind of search techniques I'm going to talk about to find some of them. Depending on how long you look and how many resources you dedicate to finding a solution, you might end up with one which is just really bad. But similarly, you might also get some good ones. Ultimately, you're trading off time spent looking for a solution, and memory, and compute power, and all that kind of stuff, for the quality of your solution. Okay, so that's what a heuristic is, a reasonable solution to a problem. How do we find heuristics? The answer is with, of course, meta-heuristics. There are lots of different types, and ultimately what they boil down to is these are ways of searching a really big search space. Imagine you've got all the possible solutions to your really difficult problem, like a bug-finding algorithm, or a fuzzing algorithm, or an IDS rule to stop people from sending viruses across the wire, or something like that. If you can just represent them as a point on a line, and you can vaguely measure how good of a solution that is, you're going to end up with a really awful graph. Sorry, I suck at paint. In real life, obviously, unless you've got how many is that? 7 different possible solutions? It's going to be a lot more volatile, right? Anyway, imagine you've got a weirdly nice looking search space like this. You can see, some solutions suck. One solution is the best, and there are a few others which are vaguely good, right? So, what you can do is you can use a technique called hill climbing. You pick a random solution on this graph. Say you pick this one. You end up about here. What you do is you take a look at your neighbors. Okay, what is the solution over here like? And what is the solution over there like? Is this one better than this one, and also better than where I am currently? If so, move across. If we go back to the graph, you start moving up this hill. And eventually you keep running that algorithm until you end up here. It's like, well, the neighbors next to me both suck harder than I do. Therefore, return. This is the solution I'm going to use. And you have a reasonable solution. Might not be the best, but it's fine. And you can celebrate with your dog and your wine. However, what if you're stuck, here? Great, I've got this solution. Wonderful. I have to drink that fake wine that Marcelo was talking about. What you can do is use a variation of hill climbing called simulated annealing, which is a little bit like it, except you have another variable called temperature. And what that does is, the higher a temperature you're at, you haven't been running this simulation for very long, so inversely proportional to CPU temperature, you might jump around randomly, just like, well, okay, I'll look at the neighbor over here, I'll look at the neighbor over there, and I'll also check out that guy at the far side, or over here, or whatever. And then eventually what you end up doing is, you might start off here, and then randomly jump there, and then maybe here, and then back there. And then gradually, the longer you run the simulation for, the likelihood of you jumping somewhere else random drops, and so it ends up devolving to hill climbing. But you're relying on the odds of actually ending up at one of these small peaks being quite low. That, unfortunately, is not always the case. And besides, we have multi-core, right? Phones have multiple processors these days. So why just look at one particular solution? Why not look at one over here, and one over there, and see how good they are? So just generate 1,000, maybe 1,000,000, billion, depending on how big your cloud is. See how good they are, and then make them fight to the death. I'm not entertained. That was actually a really difficult image to find. I had this mental image of Rainbow Batman looking for applause, but the internet is a wonderful place. By fight to the death, what I actually mean is get the really good ones, keep them, maybe combine them to come up with new ones, maybe just tweak them slightly, and then gradually fill out like your next generation, if you like. So generate 1,000 random ones, pick the best ones, fill out the next 1,000 with tweaked versions and bred versions, and then maybe generate some new random ones too. Repeat. It's a really simple algorithm. Come up with a bunch of random solutions. See how good they are and pick the best ones. Combine the best ones, mutate the best ones, fill out with some random ones. Repeat until you've gotten bored, run out of time, or you found a solution which is sufficiently good that you don't really care about getting a better one. And there's a whole bunch of things that you can do with genetic algorithms, like come up with useless crypto vulnerabilities. But in terms of the real world, it's actually really good for fuzzing. And by fuzzing, what I actually mean is this is an American fuzzy lock, which is a type of rabbit. It's also a really good tool, and it uses this testing technique, which is throw random garbage at an API until the application crashes. I mean, exercise the application's internal state. You want to come up with some kind of test or input or some set of environmental conditions or whatever that causes the program to enter some unusual or never before seen state. And you can measure that, and you can generate test cases, which means you can generate test cases that give you a high degree of new stateness, which means you can optimize for it, which means you can use genetic algorithms. And that's cool, because if you come up with application crashes that are novel, that's an O-day, possibly. You might be able to come up with some really cool exploit. American Fuzzy Lop uses genetic algorithms and a whole bunch of other techniques to develop these kind of crashing test cases. Trophies in the American Fuzzy Lop, programs they've mounted on the wall in terms of we found critical vulnerabilities in these software includes things like OpenSSL library, GNU PG, GNU TLS, major programs that are supposed to be developed with some kind of quality. So I've heard. Anyway, if you want to do this yourself, there are a whole bunch of libraries. I've used this for my own research. It's pretty heavyweight, but it's really robust and has a whole lot of options. The tutorials are really good, and if you're doing academic related stuff, this is a good one to use because everyone uses it. And so when you submit your paper and you get a review, and one of the things they're not going to complain is, you used a library I never heard of, therefore it's rubbish, use this other one instead. Which is fine. It's not the fastest, and it's Java-based, which may or may not be a deal breaker for some of you, but it's pretty reasonable. Or you could use Python. I really like Python. I've used Inspired, which is quite cool. I don't really know anything about PyEvolve or PJPy other than people seem to like it. And because it's Python, it's really simple to get up and running. It's pretty fun. If you like coming up with genetic algorithm implementations, or rather using someone else's implementation, because that whole generate, mutate, breathe, repeat thing. All of these tools will deal with all of that for you. You just have to say, I'm looking for this kind of thing. This is how you see how good it is. And I want you to generate 1,000 of them and run for 20 generations, see what you find. You don't necessarily need to understand very much about how genetic algorithms work, and trust me, there's a lot of theory, none of which is interesting. But the tools are really easy to use. You have some kind of problem, you know what the solution might vaguely look like, you can tell a computer how to generate it, go. And then you wait, and you wait, and eventually it spits out a solution, which is fine, but what if you don't really know what the solution is supposed to look like? You know, maybe when it comes to, and keep going back to this idea of IDS rules, because who went to SteelCon earlier this year? Great. Who saw the talk by David Day and Alex Shedfield about generating IDS rules? 2 of you. Excellent, which means all this will be new for most of you. I'm not plagiarizing, I promise. So anyway, one thing you can do is there are techniques where you produce a program and you teach it how to recognize the kind of stuff you want it to recognize. You want some kind of classifier. This is good, this is bad, here is a mystery set. Is it good or bad? Neural nets are really good for that. As this diagram very clearly states, you've got 3 different layers, maybe. One set of input neurons, 1 or more hidden layers, and then some output neurons. And so, say you wanted a classifier that could give you, it just gives you binary feedback, 1 or 0, good or bad, A or B, etc. You'd only have 1 of these output nodes. Because the way it works is, you take your input, your image or your PCAP or whatever, you feed it to your input nodes, like one bit at a time. Those input nodes fire off a 1 or a 0 of their own, based on some probability which you set. I say some probability because what kind of probabilities you use is an open research question, and we'll get onto that in a minute. See those arrows coming off the input nodes? When they fire, they'll transmit their signal down each one of those arrows to what's called the hidden layer. And those hidden layers will take those 1s or 0s based off their input, and again, fire off a 1 or 0 of their own based on another probability that's unique to that node. And then finally, after potentially many hidden layers, you get output nodes who will get some collection of signals, and they'll go 1 or 0, 1 or 0, flip a coin, and output it based on their input. Just before we get started, there's a pattern in the whole field of AI and evolutionary computing and all this kind of stuff. Genetic algorithms is to actual genetics, as hot dogs are to an actual dog who's overwarm. They share terminology, but the way they're actually like, very, very different. Neural nets are a little bit different in that, a neural net, which might not look very different from this, is to our actual brains, is much like my bookcase to the British Library, except the British Library to the power of something. This is very much about being inspired by nature, rather than trying to just imitate it. So you are not going to build something that replicates a brain because you're dissatisfied with your own. The thing about neural nets is, while they're really good for classifying stuff, it is kind of difficult to know what it's actually classifying on. As a brief detour, my mentor for this talk was excellent. He's right here. He gave me loads of really good feedback. I had a line in here called the Russian base problem. And he said it's really important that I actually explain what that is, rather than just having it here. So I'm going to explain it now. The Russian base problem US military, I think it was the National Reconnaissance Office, they wanted to identify camouflage Russian bases from satellite imagery. Really important. So they built a neural net, and they had a set of images that they knew contained hidden Russian bases, and they had another set of images that didn't. And they fed it through to the classifier and saw how it behaved under both sets. It's like, okay, it's doing pretty well. Here's another set where we know what the answer is, but the neural network doesn't. How does it behave with this third set of data? Okay, fine. And then they tried to run it, and it was rubbish. Absolutely awful, and couldn't spot hidden Russian bases. And it turned out what the neural network was actually doing was looking at the images and spotting which satellite took the photo. Because they had the satellites over Russia, where they knew the Russian bases were, and that had a lens flaw which made the images look a certain way, and the ones which they knew didn't have hidden Russian bases, well, at least I assumed they knew they didn't have Russian bases, were over the US, and that had a different satellite with a different lens flaw. And so it's important to make sure that you actually have a clear idea as to what your classifier is doing. Two people who did know what their classifier was doing was David Day and Alex Sheffield from Sheffield Hallam. And their problem was, how can we get Snort to tell the difference between shellcode coming over the wire from presumably people doing the same job that a lot of us are doing, slash actual blackouts, and things that look like shellcode, like JPEGs and DLLs. Any ideas? They came up with the smart idea of just getting a computer to figure it out. So they generated a neural network, gave them the known bad PCAPs and known good PCAPs to see how the neural network behaved. Gave it the unknown set of packets. They knew, but it was a mix. Saw how the neural network did with that third set of data, and then decided whether or not they needed to change anything here. Repeat. In terms of actually coming up with numbered input neurons, number of output neurons, the weightings, probabilities of firing, and the number of hidden layers, they actually used the kind of like metaheuristic stuff we were talking about earlier, the genetic algorithms and stuff, to generate the neural networks to then do this other stuff. So these techniques work really well together. So you have your known bad, you have your known good, you have mystery packets, magic goes here, and an answer falls out. How this actually works, I'm not an expert in neural networks, but my understanding is we don't know. They seem to work, and we're all carrying them around in our heads, mostly. But in terms of how to actually construct them to solve a specific problem that we know about is very much an open research question. But ultimately, all of this kind of stuff boils down onto two things. Can you tell if you got the answer mostly right? And can you compare two solutions and see which one is better, even if they're both wrong? If you can do that, metaheuristics might be for you, which is great. In terms of actually figuring out which one to use, that's a little bit more difficult. It requires a lot of information about what the problem you're trying to solve is. If you have two very similar looking solutions with very different fitness characteristics, like one's really good, one's really bad, but they're almost identical, then you probably don't want to use something like genetic algorithms, which relies mostly on small tweaks and combining of two good ones. Because if you've got two similar solutions that behave very differently, why do you think that combining them would give you something better? So what you can do is use something like genetic algorithms to try a bunch of different metaheuristics to generate solutions, and then see which solution finding algorithm works best at finding solutions. Yeah, difficult. Also, another area of very, very active research so you don't really need to worry about it. Hence the seriously. I have been working on this stuff for about 2 years now, and I have never found a single case where this seemed like a good idea. But there you are. Anyway, so general takeaway is hopefully this talk has convinced you that some of these techniques are not too difficult to understand. If they seem difficult to understand, the fault is with me, not the technique. So I'm sorry. But if you do have any questions, you can either ask me by email or abuse me on Twitter, or if you think other people would benefit, ask me now. Thank you. So, any questions? Anyone? What's your question?
So, there's obviously a lot of tech companies out there just looking at all the sponsors, and they're all doing threat intelligence, they're doing all sorts of wonderful things. It sounds like the field you're looking at there is absolutely what they should be applying in their back end. I'm just thinking about threat intelligence as a sideline, because you're pulling data in from all over the show, and you don't know where that data is. Could be good, bad data, whether it's a bad threat actor. You actually don't know, and you're hoping you classify a layer in the middle that's actually going to make it out for you. And it's exactly what you're talking about. Is industry actually taking that seriously and using it?
Well, my understanding is that David and Alex were doing this on behalf of an industry client, and I can't remember. Do you remember who it was? Okay, I think it might have been a major comms person. I personally can't remember. The answer is almost certainly not really. But at least a few people are, and that's important, because ultimately, generating a lot of this stuff just requires knowing how to configure the tools properly, and that's really straightforward. So really, anyone who has to come up with interesting IDS rules, or maybe coming up with like behavioral heuristics for antivirus, this is exactly the kind of thing which they could at least be exploring. I mean, part of the problem is you can't guarantee how good your solution is actually going to be. You can just say, keep going until it's good enough, and then wait potentially months, years, I don't know. So, but it's at least worth a shot, right? It's not too difficult.
That's what security research is for, isn't it?
Yeah, exactly. Yeah, there you go. As far as threat intelligence is concerned, that's interesting, because if you're trying to spot malicious behaviors from a network point of view, you don't necessarily know what a malicious behavior looks like. If you just look at individual packets, that's not necessarily very helpful. If you have something like a neural network, chances are they're going to be able to spot things which we as humans won't, because we just don't work that way as far as our brains are concerned. It could be literally a case of malicious traffic tends to have the bits in these positions XORed with the bits from the immediately preceding packet in these other positions, all XORed together equals 0. I don't know, maybe that's true. But that's not something which a human is going to be able to spot. That's something which a really stupid and naive classifier might. Anyway, any more questions?
If we're interested in reading up more about this, do you have a good recommendation on an introduction to the subject?
Absolutely. So, the evolutionary computation in Java. Here we go. Just show you. Oh no, everyone's going to see my search history.
xxx.com.
No one's going to be like, well, I'm not actually linked to wireless. That's probably a good thing. This is actually my second security conference ever, like industry security conference. There's been a couple academic ones. They're a lot less interesting, a lot fewer T-shirts and beer. Okay. So this is the homepage for ECJ. It looks like an academic webpage. I'm sorry. However, this book, Essentials of Metaheuristics, is actually really, really good. The guy who wrote it is, he is an academic, but he's a very good communicator, and that book's pretty good. Plus, it's free. If you want non-free resources, this book, not that edition. Okay. Anyway, anything by this guy, John Koza, is going to be. Here we go. This is the edition I have. This book is about this thick and tells you everything you need to know about genetic algorithms and lots of stuff you don't. And so if you really want a resource for learning about genetic programming that looks good on the desk, that's one. However, in terms of actually learning stuff, I wholeheartedly recommend going to the ECJ website and doing their tutorials and reading the Essentials of Metaheuristic book. Because it's like a 200-page PDF. It's,
Can you tell something about results you have with like generating ideas, rules, and stuff you did? And have you tried maybe other algorithms, other classifiers like SVMs, narrow Bayes, or stuff like that?
Bayes is an interesting one. I haven't, but I am going to. The kind of research I've been doing, and this is brand new unpublished research, so it's not quite nowadays, but you're the first people to hear about this in the vaguely official capacity. The kind of stuff I've been doing for my PhD involves attacking ciphers. And the way that classically you attack a block cipher, which is just a cipher that takes a fixed input, does some stuff to it, spits out a fixed length of copy. The way that you classically attack those using techniques called linear or differential cryptanalysis is essentially you have some kind of relationship between the message and the final round of doing stuff to your message. Because what you then do is you guess part of the key, part of the secret. You kind of partially decrypt the encrypted message that you have, and then you see whether that relationship holds between the message, the real message, and your like potentially partially decrypted intermediate ciphertext, I suppose. And if this relationship that you already know exists holds, or doesn't hold, with some probability that's different from just random chance, that means you have the correct round key, because that relationship is holding. What I'm trying to do is use genetic algorithms to come up with types of relationship. So, it doesn't know anything about linear cryptanalysis, it doesn't know anything about differential, it just has, I have these functions which I can chain, like XOR, and add, multiply, divide, subtract, etc. And I've got some data points. I've got the message, I've got this partially decrypted output, I've got the key. What can I come up with where, what kind of relationship can I construct that behaves one way when you guess the key correctly and a different way when you guess the key incorrectly? Because that way you can actually try and apply that relationship, try and guess the key. And and you should be able to tell whether your key guess is correct or not. Because if you can tell that your key guess is correct for that one small part, it means that instead of having to guess all of the key at once, you can guess one part and then another, and that's way faster. So that's the kind of stuff I've been doing. And the end result is, and this is kind of an example of why metaheuristics are weird, I rediscovered linear cryptanalysis. Yay. I also found that the way my program currently works is it seems to get fixated on a statement where this relationship always evaluates to true with this message and this ciphertext if the key is in this set. And it always equates to false if the key is in that set, which gives you one bit of information, i.e. your key is in that bucket, or it's in that bucket. And so I'm currently kind of stuck, because I can either try and changed the code to look at more general purpose approximations, like it gives you maybe the same, gives you one bit of information per key pair, and then you can have multiple key pairs and figure out the key is exactly this. Or come up with a whole sequence of statements where it's like, okay, well this statement tells me the key is in that bucket, and of that bucket, this statement tells me it's in this half of that bucket, and so on, and turn the search for a key into what's called a binary search. Which again is a lot faster. It's like looking a key up in a dictionary rather than having to have lots of plain text and stuff. But that's all forthcoming in terms of actually getting useful results. But yeah, in terms of actually coming up with actually useful security results, I haven't done any of that yet. But other people have, and hopefully some of you guys will. Any other questions? I understand that I'm the only thing between you and also me and coffee. Anyone else? Well, thank you very much.